Hello there, hello and welcome to this talk, which is fully serverless, a case study. So I'm Stephen Colebourne, engineering lead at OpenGamma, created various projects, Java champion. This is Chris Kent, who will be presenting the second half of the talk. He's also an engineering lead at OpenGamma, comes from a finance background. So OpenGamma, it's a fintech startup. So our customers are generally banks, hedge funds, pension funds, these kind of companies. Based in London, New York, and we're there producing cloud-hosted analytics for these banks and hedge funds. So big calculations that they need doing, and we host those in the cloud. So you don't need to know details about what those calculations are, because not all of you will be in the finance industry. So we started building our new platform on AWS, and we started building that in about 2017. So as a result, serverless was available. So we kind of haven't ever really had big cloud-hosted monoliths. As a result, we took a choice to go fully serverless. So in essence, we're one of those relatively few companies out there that have tried that as an approach. Hopefully this will give you some insights onto some of the things we've found. And underneath it all, we have an open source library. So if you do work in finance, you can look at our open source library, which allows you to calculate various of these analytics just as a Java library on Maven Central Strata. Okay, so we'll be covering various bits. I'll be introducing sort of serverless, and then covering our data services, and then Chris will cover sort of margin service, analytics service, and the more ops and infrastructure parts. So what is serverless? Well, lots of people have lots of different definitions of it. Ultimately, we kind of have gone down the route of basically thinking, it's if you're not thinking too much about the infrastructure, if your infrastructure is essentially invisible to you, if you don't know where that code is running, or you can't control where that code is running, then that is in effect serverless. So we're all AWS. Obviously, there are serverless parts on the other big platforms. But on AWS, life started with EC2, which is just infrastructure as a service, and then it kind of built out. So you had containers as a service, Elastic Beanstalk for this platform, and then up at the top we've got Batch and Lambda. So Lambda is what we'll talk a lot about today, which is function as a service. Kind of. Servers at one end, serverless at the other end. Now, if you're looking closely, we've got Batch up there, and we'll talk a bit more about Batch and how we find that fits in later. So AWS Lambda itself, ultimately, what you're doing as function as a service is you get given an interface, and that's a single method interface. In this case, there are a couple of options, but the lowest level one is fundamentally handle request. Here's an input stream. Here's the output stream you're going to write to, and here's some contextual information about it. Now, that method, whatever you write to implement that interface, is going to get called by the framework, called by the AWS system when it needs you to do some work. And that's about the extent of your interaction with servers. What you're going to do is you're going to write a class. It's going to implement that interface. We're going to return hello world. We're going to package that up as a jar file, where that jar file includes all the dependencies, Maven jar with dependencies. And you're just going to upload that jar file to AWS, and then AWS can run it. So whenever you invoke that Lambda, you'll get back hello world. It's not dissimilar to servlets, but you don't have to run the server yourself. One assumes that somewhere in AWS they have a whole heap of code that's not unlike an application server and is capable of instantiating your class and running it. But you don't need to know about that. You don't see it. So AWS Lambda is handling your compute needs, but if you're going to go serverless, you've also got to use other things as well. So if you want to store in a database, well, we use DynamoDB. It's AWS's own lightweight JSON-based type data store. There are other databases available on AWS. API gateway, so this is where you have REST APIs coming in from the outside world, from the public internet. They're going to come in via API gateway, which is going to provide certain filtering, denial of service protection, just general API-ness, and that will then call on to your Lambda. If you want to store big files, well, DynamoDB has a limit in terms of how big the files are you can store in it, but S3, you're a global hard disk drive, basically, so you can store any old file you like on there. And of course, you're going to need logging. Now, all of these are, effectively serverless, as in you don't really know where any of this data is being stored. So with OpenGamma, we sort of, for the purpose of these talks, we're grouping our system into sort of three conceptual areas. The analytics part, where we actually calculate, the high-level numbers that people want to care about. The margin service, where they calculate the middle-level numbers. And then the data service, where we collect and package up and make available lots of data that is necessary to do the calculations. For example, what is the FX rate between British pounds and US dollars recorded over a long period of time? That's the kind of information you're going to need. So in the data services part, it's reference data and market data for the rest of the calculations. So reference data means it doesn't change very much, and market data is stuff that's changing all the time, so stuff that's changing daily, like those FX rates. Now we get hold of this by downloading it from key industry providers. So there are companies out there which you may well not have heard of, but companies like LCH, CME, Eurex, JSCC, these are big companies, and they can provide us with the kind of data that we need. So what we need to be able to do is to pull down that data and then post-process it. Now, if you've not worked with a serverless system, you might imagine how you might write a server and how it might check an FTP site and pull down some data, and then when that's pulled it down, it can do some processing, and you might use lots of threads to do all that processing. So the question is, how does all of that translate across when you haven't got quite the same ability? Okay, so the approach we took was, how do we know the data's on some remote website, some remote FTP site? Well, we kind of don't. So as a result, what we do is we poll every 15 minutes to get that data. So we use CloudWatch events, is a thing in AWS that allows you to trigger an event every 15 minutes, every 5 minutes, whatever. So CloudWatch events triggers every 15 minutes, and through the magic of AWS, it will trigger your Lambda. And that Lambda is just a piece of Java code in a jar file implementing that interface. So you'll get triggered. The context will say, I've been triggered by CloudWatch events, and provide some other security information. And then within that implementation, within that class, obviously you can kind of do whatever you like. And the do whatever you like is, go away, pull the data down from the FTP server, check that it's all there, make sure it's okay. And then the way we do it, because the data tends to be large, we store the data itself in S3, and we store metadata about the data in DynamoDB. So we can come along later and look up in DynamoDB to get the information in order to find the record in S3. Nice, straightforward thing. There are other ways to trigger a Lambda. So, here we saw that CloudWatch events was triggering a Lambda, but you could also have your Lambda triggered whenever you save a file in S3. So whenever you save a file, you get an event to say something happened. Whenever you update a row in the DynamoDB table, you can get an event and you can process it with a Lambda. Whenever you get a REST API call, you can trigger a Lambda, or from a queue. So there's lots of different ways in which you can trigger Lambda. It's just a generic little piece of code that you can run in response to some external event. So now we've downloaded our data from some FTP server and put it into S3. We now need to do some post-processing on that. Now, we could do the post-processing in the first Lambda that downloaded it from FTP. But Lambdas only live for 5 minutes maximum. Now, it turns out that's probably not quite enough time to do all the post-processing that we want to. particularly if we want to do 5 post-processing events on one download. So what we need to do is essentially have one Lambda that does the download from FTP and then trigger off 5 different Lambdas to do 5 different kinds of post-processing. So how do we trigger the post-processing? Well, we could do it such that when you write the row to the database in DynamoDB, it comes back and that's the trigger. That would be one possibility. We could write a message to a queue when we've finished the first Lambda. We could directly trigger the other Lambdas. There are various solutions. We chose a nice simple one, which was because we haven't got any urgency. This kind of stuff is happening at midnight. So we, again, just poll every 15 minutes. Poll every 15 minutes to see, did the first one complete? If so, let's do some post-processing. What does the post-processing look like? Well, it's a Lambda. And that Lambda, the first thing it has to do is call out to a different Lambda. And that Lambda's responsibility is to read the metadata. And then when we've read the metadata, what we were doing is we were returning the location in S3 where the actual data is. But then it's the responsibility of the first Lambda to go and actually get it out of S3. Now you might think that second Lambda, the one on the right, would go to S3 and return it to the first one. But there are limits on the amount of data that you can pass into a Lambda and you can return from a Lambda. And our files are too big. So therefore, all we can do is pass back the location in S3 of the data and have the first Lambda go and get it itself. A bit annoying. And then when the conversion's finished, it's going to do something relatively similar to the first one, which is store some metadata and store the converted data in S3. So this is a standard pattern that we've adopted. Metadata in Dynamo, data itself in S3 because it's too large. When you've only got a 400 kilobyte limit, that's often not big enough. And obviously it's also the case that the bigger the row gets, the more expensive it is to use DynamoDB. The Lambda indication sends back the metadata because you have this 128K limit if you're being triggered by event. You can get up to 6 megabytes in certain modes, but ultimately it's better for the caller to directly trigger S3. It's better to pass back the location of the data, not the data itself. Now, following all this through, if you had to, write your Java code when I'm calling from Lambda 1 to Lambda 2, if I have to actually, call the Lambda and then extract out the S3 and then go to S3 and I have to manage all of this, it's quite a lot of code that's going to be repeated in multiple places. And as a result, we package that repeating code up in a little library. This is Java, perfectly sensible thing to do. So we have an interface called Industry Data Service, static method on it. We can call Industry Data Service.remote to get an instance, and then we create a request object, and we query the request, and we get back the metadata in our response, and then we have another method on the service, which is, get me the file, as bytes, and we'll get back that byte array. So if you're going to have multiple Lambdas talking to one another, you're probably going to have to spend some effort providing some nice, clean API to wrap that calling pattern. Limits. Whenever you work with AWS, one of the first things you'll do when you come across a new thing in AWS you might want to use, one of the first things you'll do is look up what their limits are, because it's all about the limits. So Lambda's limits are a 5-minute timeout. I know some big companies can request for extensions, but most of us can't. A maximum of 3 gigabytes of memory. That has gone up. It used to be quite a bit less than that. You only get 512 megabytes of disk space. That's the number of threads you get, although you don't really get that many cores. Again, you can also only run 1,000 instances of a Lambda at any one time. Again, you can increase that. And your jar with dependencies is limited to 50 megabytes. Now in Java, you hit that limit quite soon. If you put in too many dependency jar files, you find that it's too big to upload to Lambda. So we've pretty much hit all of those limits at some point during our lifetime. These limits matter. and you can't ignore them. So what happens if you hit a limit and you can't get around it? So some of the data that we're dealing with is bigger than that 3 GB memory limit. What do you do? So our approach is to use AWS Batch and to kind of treat AWS Batch as a serverless environment. Now, we can argue as to whether it really is or is not serverless, but we can kind of treat it as such. So basically, all we've done from the previous diagram is replace a Lambda with AWS Batch on the diagram. It's a bit more complicated in practice to just switch from AWS Lambda to Batch. Batch as a concept is intended for large and long-running data processing. Something you kick off, it runs lots of stuff and produces some output. The way it works is you submit a job, and then you twiddle your thumbs, and then at some point it will start running. Effectively behind the scenes, it's waiting for a bit of spare capacity on Amazon's cloud, on their EC2 cloud, and waiting for some spare capacity for it to run it effectively. Now, that's great, but obviously, it's not something you can rely on as just being it's going to happen now. So obviously, the nice part about this is, it's effectively auto-scaling. If I submit, 5 jobs, it will try and find 5 available EC2 instances for that to run on. I don't have to worry about the scaling side of it. What I've lost is the ability for controlling how quickly it starts. It's fine for us, because we don't care for this particular type of processing how quickly it starts. So you are now allowed to trigger batch from Cloud Launch events. That wasn't originally the case. So obviously, Lambda versus Batch, well, they're not really equivalent technologies. You're going to prefer Lambda because it's easier to use and it's easier to manage. Batch is a possible fallback if you hit some of the limits in Lambda. But if you need processing that occurs now in response to an event, as opposed to sometime in the next 2 to 10 minutes, then Batch is not an alternative. And in fact, there isn't an alternative. You are going to make this work, there's a concept called fetch and run. You can Google about it. But basically, it's a small Docker image that will get the jar file and run it for you. And it's that effectively turns Batch from being kind of non-serverless into something you can treat as being much more programmer-friendly and serverless. So, if we were to write our system, which effectively has 4 different services, conceptual services, you might have written, 4 servers and run, 4 EC2 instances. And instead, we've got 23 Lambdas and 2 batch instances. So some of that complexity, which would have sat within those monoliths, I don't really want to call them monoliths because they're not really that big conceptually, right? Each of these 4 services is, a couple of hundred classes, maybe, if that. They're not that big conceptually, but we've had to spread that logic out over quite a lot of different places. So that complexity that's there, that's now in the infrastructure. And Chris will talk a bit more about that in a minute. Obviously, what you're getting is that, we're using cron triggering, each Lambda is performing a small isolated task. If it fails, fine, you can run multiple of them together, which we don't particularly need in this case. The alternative approach, you have to have that Java server running continuously, but it can just try every 15 minutes by sleeping for 15 minutes to thread.sleep, nice and quick. You didn't need any infrastructure to set that up. Right, and now over to Chris.
Right, so the first of our serverless systems that I'm going to talk about is our margin service. Now, it's a financial calculation service. Its inputs are a portfolio of trades and the market data and reference data that Stephen talked about, and the outputs are the margin breakdown for those trades. It's a stateless system. The calculations are run on demand, and it's accessed through a REST API, both programmatically and via a web interface. We're currently on our third implementation of it. Originally, it was a traditional web app running in Elastic Beanstalk, so a monolith. Then we rewrote it to do some of the calculations using Lambda, and then finally we reworked it so that all of the calculations are done using Lambda. And this final step was actually quite hard, and the reason for that is that the amount of data that's used in the margin calculations. Now, a full set of margin data, in the worst case, is about 4 to 5 gig, and each individual calculation only uses a small subset of this, but the full set is huge. Now, on Elastic Beanstalk, that isn't a problem, because the data doesn't change during the day. So at the start of the day, you bring up the server, it loads all the data, and then it holds it in memory all day and uses it for every single calculation request. And that means that all the data for every calculation is in memory, and so the performance is excellent. I don't quite know what's going on with the... Now, obviously, with the move to Lambda, that approach is no longer viable, because we can't possibly load that full data set in a single Lambda. It's already, just the data alone is bigger than the memory limit for a Lambda, and it takes about 90 seconds to load, which is clearly impossible for an interactive calculation. So the obvious approach is just load the subset of the data that we need for any particular calculation, which sounds easy, but actually required an awful lot of pre-processing of the data to split it up into small enough chunks that we can load them individually on demand into a Lambda. And this also means there is no possibility of caching between requests, because each calculation will have slightly different trades, therefore it will use a slightly different subset of this data, and so we have to reload the data on demand for every calculation. So our migration to Lambda most of the effort was spent managing the data better to allow us to overcome the limits of Lambda and to load it on demand. There was a side effect of this that was beneficial, which, as we could load the data on demand, we could load the data for any date in the past. Now, with Elastic Beanstalk, this wasn't possible. We could only load 1 to maybe 3 days data at a time. So this was fine for our clients, who are primarily interested in yesterday, but for us, there are some cases where we wanted to run like a lot of historical calculations, and that would have required running an awful lot of Elastic Beanstalk instances, which clearly wasn't practical. So that was a useful side effect. It also introduced latency. Obviously, in the original server, we had all the data in memory all day. So when we moved to Lambda, that data had to be loaded on demand. That subset had to be loaded on demand, which introduced some latency, but it was manageable. The other main effect of this migration was scalability, which is probably the headline feature of Lambda. It scales up transparently to handle load, and then scales down to 0 when it's not required. And it really does work as advertised. This particular system, we have kind of a trickle of requests all day, virtually nothing at night, bar one period of about half an hour when one of our clients runs their end-of-day calculations, and so we have a huge spike. And running in a traditional server, we could simply provision a lot of hardware to handle that spike, which would then be sitting there mostly idle for the rest of the day, costing us lots of money. We could try and smooth out the spike by queuing up the requests, but obviously that would introduce latency, where with Lambda, it solves the problem nicely. So when that spike hits, AWS spawns many, many Lambdas, and so the calculations are all done in parallel, and when the calculations are finished, the Lambdas are all destroyed, and we're no longer paying for any compute that we're not using. So that works very well. Unfortunately, that wasn't the end of the story. Our calculations scaled wonderfully, but that revealed bottlenecks elsewhere in our data stores, Dynamo and S3. So it solves some of your scaling problems, but it's no silver bullet. Now, this is the setup we use for the margin calcs. So we've got API gateway for the REST API. We have one Lambda that handles the HTTP request, another Lambda that does the calculation, and the data stores. Now, the interesting part of this is the two Lambdas. Why two Lambdas? Why not simply handle the request and do the calculation in a single Lambda? Now, the problem is that margin calculations can be slow. And there is a hard limit in API Gateway where you can't hold an HTTP request open for longer than 30 seconds. Now, for a large portfolio, margin calculation can easily take longer than that. So to work around this, we treat each calculation as a RESTful resource. So a client requests the calculation, we create a resource, we return a response with a location header, with a URL, pointing to their result, and then the client polls that URL. Initially, they get a pending result, and then when the calculation completes, they'll get their full set of results. It's a standard pattern. It works nicely, but it is actually quite painful to do with Lambda. And the reason for this is that that initial request has to return quickly with the location of the result, but the calculation has to continue in the background. Now, it's quite possible to start a background task in a Lambda just like you could in any other piece of code, but when that main thread returns the response to the caller, the Lambda is suspended, the background task is suspended, and the calculation never completes. So the way we got around this is the request handling Lambda asynchronously invokes the calculation Lambda, the request handling Lambda can return the response, and the calculation Lambda continues to run in the background until the calculation is complete. Now, in Java, this would be a few lines of code creating a background task, and the request thread can return. With Lambda, it's now an infrastructure problem. We have to create an additional Lambda, and we have to wire the two Lambdas together. So what is quite an easy task in a traditional server suddenly becomes a lot more painful. Now, our REST API in front of the margin service is also serverless. This is built with API Gateway, which defines all the API endpoints, and then the request handling logic when an endpoint is invoked is done using Lambda. It fits our use case nicely. It's a very traditional web app. It's got no state in the request handling code. All the state is in the data stores. So it fits nicely. Unfortunately, it isn't actually that simple to use. API Gateway it's verbose to configure, it's complicated, and it's quite an unfamiliar model. And the integration with Lambda is pretty low level. It doesn't have any of the HTTP request and response abstractions that you're used to from most Java web libraries. And our first reaction when we saw this was, surely there must be a library. It's such an obvious problem, and REST API is defined in code. It's a solved problem. But when we started this, I don't know, a year and a half ago, that wasn't the case. There was nothing on the JVM that we were happy with, so we created our own very simple library, inspired by JAX-RS. So we define a class with one method per endpoint with a annotation defining the path. Then when the request comes in, our library code looks at the path in the request, it looks at the path on each of the handler methods, and chooses the method to handle the request. If we were starting this now, we probably wouldn't need to do that. There are more choices now. The first one is AWS SAM, their serverless application model, which is basically a pre-processing layer that sits on top of CloudFormation, which is their service for declaratively defining your AWS resources. It's still quite low level. You still don't have any nice HTTP abstractions, but it's a huge step forward from what was there before. Much more recently, AWS have introduced AWS Serverless Java Container, which is a snappily named open source project that allows you to embed the familiar Java libraries inside your Lambda. And so it supports Spring, Spark Java, and Jersey, last time I checked. And it provides a bridge between API Gateway and Lambda's low-level view of HTTP to the familiar HTTP abstractions that we're used to. And finally, there's my own library, Osiris, which I wrote in frustration when we first started this. It aims to be high level still, and it has a Kotlin DSL to define the API and the request handling logic, a local server to make it easier to develop and debug, which is another pain point I'll come to, and Maven and Gradle plugins that generate all the AWS config and do the deployment. Now, it's not without challenges building an API this way. One of the most obvious ones is the cold start time. So when you're using the Java runtime in AWS Lambda, when a Lambda is created, it has to create a JVM, which is not a lightweight process. It takes, a couple of seconds, sometimes more. It's not the end of the world, but it can be noticeable. What is not guaranteed about Lambdas, but in practice, they are actually reused. They're not destroyed as soon as they return. They're actually kept around for 5 minutes, 10 minutes, up to an hour in some cases, I think. And you can take advantage of this. So if you keep poking a Lambda, making it run a little bit of code every few minutes, then AWS will keep it alive. And then when you get a real request from the outside world, that Lambda will be available and warm and can service the request without any of this startup delay. Now, none of this keep alive behavior is guaranteed by AWS. A Lambda can be destroyed at any moment. So it feels like a bit of a hack to be relying on this, but it's pretty common. An awful lot of people do this, and it seems to work, and it solves the problem. The other major challenge, which I mentioned earlier, was development workflow. Now, if you define your API using API Gateway, you obviously have to deploy it to AWS to be able to test it. And that deployment is not trivial, can take a little while. It's obviously much harder to debug. And if you don't have an AWS environment set up for every single developer, then inevitably you'll get contention when two people have two different sets of changes and they want to test them at the same time on the dev environment. In the end, this got so painful that I built a local server using Spark Java that it recreated all the endpoints from our API Gateway config and invoked our Lambda logic directly. It's painful to have to do that, but it was worth it for the problems it solved. Nowadays, we probably wouldn't need to do this. The libraries I mentioned earlier would all support this out of the box. If you're using Spring, then you could run that locally and also deploy it to AWS. So comparing this to what we have now with Lambda to what we had originally with Elastic Beanstalk, we have taken one monolithic code base and split it up into 9 separate Lambdas. So we've introduced some complexity. We have to pre-process all the data to split it up into small chunks that are manageable for a Lambda. But as I mentioned earlier, arguably we would have needed to do this anyway for historical calculations. And we have scalability. We have extremely good scalability, whereas before we couldn't scale nearly so easily. You can scale Elastic Beanstalk, but that requires some manual intervention. With Lambda, that just comes free. Our other serverless system is our analytics service. It is similar to the margin service in many ways, as it takes in portfolio data, market data, reference data, and performs a load of calculations on it. The important difference is that it performs an awful lot more calculations, so many that it's not practical to do them on demand. So we run these as a batch job, and we store the results in Dynamo and S3, as Stephen explained. And we have a web interface backed by a REST API built in exactly the same way as the one for the margin service. One of the biggest considerations for this service is data security, because the inputs include clients' portfolio data. So this is hedge funds, investment banks' portfolio data. The results include data about their positions. Now, this is highly sensitive data. They're extremely nervous about this data getting leaked. So from our point of view, if we were to leak it, if we were to send data from one client back to a user from another client, it would be potentially disastrous. So to reduce the risk of this, we strictly segregate the data for every client. We use encryption for all clients' sensitive data. Every client has their own encryption key used to encrypt their data. In some cases, this is actually managed by the client themselves in their own AWS account. They can grant us permission to use it, and that gives them the freedom to revoke our permission at any time, and then we would be unable to decrypt their data. So that gives them an extra level of comfort. And this fits quite nicely with Lambda, because the way we've got it set up is any given Lambda is invoked for one client, and so it only ever deals with data for one client, it only ever has credentials for one client, it only ever has access to the encryption key for one client. So even if we made some sort of programming error and loaded the data for the wrong client, it would fail. We wouldn't have access to the decryption key to decrypt that data, and so we couldn't even return it to the client. We'd never even get it out of the data store. And using lambdas allows us to structure the code in such a way that it would be very hard to make an innocent mistake and return one client's data to a different client. And this shows roughly how that's achieved. We have the role for the client, and that role is used by the Lambda and controls access to all the resources containing the client's data. So if we were to write this as a traditional server, we would, in order to get the same level of data segregation, we would need one server per client. Now, clearly, that is a lot of infrastructure to manage. It doesn't scale at all well for multiple clients. Alternatively, we could have one server that handles all clients together, but then we would have to be extremely careful, and it would be much easier for an innocent coding error to lead to disaster. So now I'm going to talk a bit about how we build and deploy, run, and monitor our code. We have a continuous integration and deployment pipeline that deploys directly to AWS. It's controlled by files that are checked into GitHub. So we have, for each environment, we have a different file, and that file contains a list of all the components and the corresponding versions that are currently deployed. So for our dev environment, typically it will just be pinned to the latest version. So whenever anyone merges a change to master, it's automatically picked up and deployed straight to the dev environment. For production, that versions file will typically contain the tag in Git of each of the components. So when we want to do a production deployment, we tag the code, we upload it to a test environment, we test it, and then when we're happy with it, we update the tag in the production versions file. That gets reviewed, merged into master on GitHub, that's picked up by the deployment pipeline, and everything is deployed to production. The pipeline is made up of GitHub, which stores the files, Shippable, which is a build service which checks out the code from GitHub, builds, runs the tests, and uploads the artifacts to S3. Then AWS Code Pipeline, which is their deployment pipeline service, that detects when the artifacts hit S3, and it then invokes some of our custom code in yet another Lambda that parses the versions file, compares it to the currently deployed versions, and deploys any components that are out of date. Now, in a system like ours, which is highly distributed, obviously logging can be an issue because we have many, many components, so we have many, many logs. And so when we have an issue, it can be hard to find the actual log event related to that issue. Everything logs to AWS CloudWatch Logs, which is their standard logging service. There's one one log stream for every single component, and all our many components logged to their own log stream. So first of all, that makes finding the actual log event quite hard. Secondly, the usability of the CloudWatch Logs console isn't great. It's quite slow, it's quite hard to search for anything. So we also use a product called Sumo Logic, which is a third-party log aggregation service. We have a Lambda that periodically copies our log events from CloudWatch to Sumo Logic. That gives us much more powerful querying, much more powerful and much faster querying than we can get in CloudWatch, which takes advantage of structured logging. So our log events, rather than just containing free-form text, mostly contain a JSON object. And Sumo Logic compiles that JSON, and those fields from the JSON can be used in the search queries. Now we have two different approaches for monitoring and alerting. The first one is CloudWatch Metrics, which is it's a standard AWS service, monitors high-level metrics about all your components. So, the count of failures for a particular Lambda, the count of error statuses returned from a particular API, and so on. These can be set up to trigger alerts. If you get a particular number of these metrics counted in a particular time window, then you can trigger alerts. I don't actually find these particularly useful because they're very vague. It just says, effectively, something went wrong with this component in this time window. Off you go and figure out what it was. So we also use Sumo Logic for alerting. Now, a Sumo Logic alert is effectively a Sumo Logic query that is run over the incoming stream of log events. And similarly, if it has a number of matches within a certain time frame or doesn't have a number of matches within a certain time frame, we can raise an alert. It's much easier doing it this way because the alerts are triggered directly by the log events, and so it's much easier to find the log event that triggered a particular alert. Now, infrastructure is obviously a challenge when you've got a system built from so many small components. So it wouldn't be feasible to manage all of this by hand in the AWS console. So all of our infrastructure is defined as code. We have configuration files that define all the resources. These are stored in GitHub, so they're versioned, they're reviewed. Allows us, if we need to rebuild an environment from scratch or build a new environment if we need to. We use Terraform for this, it's an open source project that supports most of the cloud platforms. If you're solely on AWS, then AWS has CloudFormation to do the same thing. Arguably slightly better integrated with AWS, always has support for their new products when they're released, whereas Terraform can lag slightly. Terraform, it gives us two things. It gives us this declarative format for defining all our resources, all our Lambdas, all our database tables, S3 buckets, everything. It's JSON-like. And it gives us a command line tool that allows us to diff the current state of the running system against the current state of our config, show us what changes we would apply, and then gives us the tools to apply those changes to the environment. The config is quite verbose, it's quite fiddly. This is a reflection of the underlying AWS model. Now I've done the same thing with CloudFormation, I've done the same thing using the SDKs directly, and it's the same in all cases. It's fundamentally quite a complicated underlying model, and Terraform simply exposes this without layering any high-level stuff over the top. Terraform can be a bit flaky, but we're mostly happy with it. It does the job. So, to wrap up, serverless has definitely we've found it's got costs and it's got benefits, and we've definitely felt the pain and we've felt the benefits. Very much depends on your use cases. The biggest cost, as far as I can see, is the complexity that it introduces. Assuming your system has an intrinsic amount of complexity, if you build it from a lot of very small, simple components, then the complexity has to go somewhere. And our experience says at build time, that's going into the infrastructure, and at runtime, it's going into the interactions between all these components. There isn't a high-level overview of our whole application. If we had a single monolithic code base for each for each of our services, then we have very mature tools to introspect that. We can see what our dependencies are, we can see what calls what. We don't have that anymore. Lambdas call lambdas, and it's very hard to see which lambda calls which lambda. Monitoring and alerting, as I said, is much harder because everything is so much more spread out. And obviously, lambdas have very restrictive limits, as Stephen mentioned. And when you hit these limits, say like when we moved from Lambda to Batch for our calculations, it's a big step. You can't simply take the same code. All we wanted was to run that same code, use more memory, run it for a bit longer. For us, that should be easy. Unfortunately, we had to move from one service to another service, move from deploying as a jar to deploying as a container. It's a big step. It feels like something's missing there. The benefits of serverless. Obviously, the clue is in the name. We don't have to run any servers, and that really is great. It's one less thing to worry about. It does transparently scale as well as you'd hope, and scales down to 0 when it's idle, so saves us a lot of money and lowers the barrier to entry. There are some apps that wouldn't be worth writing if you had to manage a server and pay for a server, but with serverless, those apps suddenly become viable. It makes data segregation much easier, and it's a very simple programming model. It's just a jar file, and it's just a function. So, to wrap up, it can be great, it can be painful. We've experienced both sides of it. It feels like some convergence is long overdue. Our example of moving from Lambda to Batch, that was a big step. It feels like there are missing pieces to the puzzle that could make this a lot easier. And the technology is young. A lot of the problems we hit are not intrinsic problems with the serverless model, but more limitations of the actual serverless of AWS Lambda. And these limits are moving all the time. The memory limits, as Stephen said, the memory limits were doubled recently. These limits are likely to be improved further and further. And tooling is the other pain point. Now, given the excitement around Lambda, it's clear that the tooling is going to improve. So, it's very likely that things can only get better. Thanks.
Cool. So we only have 3 minutes left, so rather than taking questions publicly, I suggest you guys come down and ask us any questions you've got. Thank you.